In this video, we're going to continue our discussion of power series functions. Given the power series for log of 1 plus x is equal to summation n equals 0 to infinity minus 1 to the power of n times x to the power of n plus 1 divided by n plus 1, evaluate the integral x squared log of 1 plus x to the fourth dx as a power series. So our job is to use the power series for log of 1 plus x, algebraically manipulate that to find the power series for the integrand, and then integrate term by term to find the power series for the integral. Part B, use part A to approximate the definite integral from 0 to 0.5 x squared times log of 1 plus x to the fourth dx, accurate to within 10 to the power of minus 7. Let's do part A first. So we have log of 1 plus x is equal to summation n equals 0 to infinity negative 1 to the power of n, x to the power of n plus 1, divided by n plus 1. So let's find the power series for log of 1 plus x to the fourth first. So log of 1 plus x to the fourth. We're going to put x to the fourth inside for x. So we're going to get summation n equals 0 to infinity minus 1 to the power of n, x to the power of 4 to the power of n plus 1, divided by n plus 1. Now we need to get the power series representation of this integrand first. So we're going to multiply both sides by x squared and multiply this side also by x squared. All right, let's do the algebra. So what we have is log of 1 plus x. Log of 1 plus x is equal to summation n equals 0 to infinity minus 1 to the power of n, x to the power of n plus 1, divided by n plus 1. Now plug in x to the fourth for x, so we get log of 1 plus x to the fourth is equal to summation n equals 0 to infinity minus 1 to the power of n, x to the power of 4 to the power of n plus 1, divided by n plus 1. Let's simplify this, and we're going to get summation n equals 0 to infinity minus 1 to the power of n, x to the power of 4n plus 4, divided by n plus 1. Now multiply both sides by x squared so we can find a power series for the integrand x squared times log of 1 plus x to the fourth. So multiplying both sides by x squared, we get x squared times log of 1 plus x to the fourth is equal to x squared times summation n equals 0 to infinity minus 1 to the power of n, x to the power of 4n plus 4, divided by n plus 1. Let's multiply x squared inside the summation, and we're going to get summation n equals 0 to infinity. We have the same base, so the exponents add up. Negative 1 to the power of n, x to the power of 4n plus 4 plus 2, so we get x to the power of 4n plus 6, divided by n plus 1. Now we have the power series representation of the integrand. And the next step, of course, is to integrate both sides and get the power series representation for the integral. So we're going to integrate both sides, so integral of x squared, log of 1 plus x to the fourth dx. So we're integrating the function, and now on the right-hand side, we integrate the power series. So integral summation n equals 0 to infinity minus 1 to the power of n, x to the power of 4n plus 6, divided by n plus 1. Integrate all of this with respect to x. All right, let's do that. So we have integral x squared times log of 1 plus x to the fourth dx. This is equal to integral summation n equals 0 to infinity minus 1 to the power of n, x to the power of 4n plus 6, divided by n plus 1 dx. So integral of the sum is sum of the integrals. So we rewrite this as summation n equals 0 to infinity, reverse the order of integration and summation, and negative 1 to the power of n divided by n plus 1 is a constant, so that just stays in the front, and we integrate the part that involves x. So integral of x to the power of 4n plus 6 dx. So we apply the reverse of the power rule to get this antiderivative. So we get summation n equals 0 to infinity minus 1 to the power of n divided by n plus 1. Add 1 to the exponent and divide by the same. Reverse the power rule. So we get x to the power of 4n plus 7 divided by 4n plus 7. And don't forget to add c. So we now have the power series representation for the integral x squared log of 1 plus x to the fourth dx. Now let's expand this term by term. So we have integral x squared log of 1 plus x to the fourth dx. We're going to expand the power series term by term. Plugging n equals 0, we're going to get n equals 0, we'll have x to the power of 7 divided by 1 times 7. Plug n equals 1, we get minus x to the power of 11 divided by 2 times 11. Plug n equals 2, and we're going to get x to the power of 15 divided by 3 times 15. Plug in n equals 3, and we're going to get x to the power of 19 divided by 19 times 4, plus c, of course. And this is an infinite series, so it goes on. All right, so now we now have the power series representation for this integral. We've written it in compact summation notation, also in expanded form as well. Part B asks us to evaluate the definite integral from 0 to 0.5 x squared log of 1 plus x to the fourth dx. So we need to apply the fundamental theorem of calculus, fundamental theorem of calculus. So we can use any antiderivative. So why not use the antiderivative of the previous exercise with a constant c equal to 0? So we found integral from 0 to 0.5 x squared log of 1 plus x to the fourth dx. We can use any antiderivative, so we're going to use this antiderivative, but the constant c is going to be 0. So we're going to take this constant to be 0. All right, so we get x to the 7 divide by 7 minus x to the power of 11 divide by 22 plus x to the power of 15 divide by 45 minus x to the power of 19 divide by 76, and so on. Evaluate it from 0 to 0.5. Now let's put the upper limit in and evaluate this integral. So we have integral from 0 to 0.5 x squared times log of 1 plus x to the fourth dx is equal to, putting 0.5 in for x, we're going to get 0.5 to the power of 7 divide by 7 minus, into the second term, 0.5 to the 11 divide by 22 plus 0.5 to the power of 15 divided by 45 minus 0.5 to the power of 19 divided by 76. All right, so we're going to apply the estimation theorem, the alternating series estimation theorem, to estimate the sum accurate to within 10 to the minus 7. So let me rewrite this because it got a little bit tight here. So we have 0.5 to the power of 7 divided by 7 minus 0.5 to the power of 11 divided by 22 plus 0.5 to the power of 15 divided by 45 minus 0.5 to the power of 19 divided by 76, and so on. Now, this infinite series is the exact value of this definite integral. But our job is to find an estimation, to find an approximation accurate to within 10 to the minus 7. So we know that by the alternating series theorem, if you add the first n terms, the error is less than the n plus 1th term. So if we add the first 3 terms, the error of this sum would be less than the absolute value of the 4th term. So let's look at the 4th term and see if it's less than 10 to the minus 7, then we'll just add the first 3 terms. All right, So looking at the fourth term is minus 0.5 to the power of 19 divided by 76. So absolute value of minus 0.5 to the power of 19 divided by 76. Putting this into the calculator, we obtain 0.0000, 4 zeros, and another 3 zeros, 25. This is definitely less than 10 to the minus 7. So that means the integral from 0 to 0.5 x squared log of 1 plus x to the fourth dx can be approximated by the sum of the first three terms, because if we add the first three terms, the error of the approximation is less than the fourth term, which is less than 10 to the minus 7. So the error will be less than 10 to the minus 7 if we add the first three terms. So the first three terms of this infinite sum is 0.5 to the power of 7 divided by 7 minus 0.5 to the power of 11 divided by 22 plus 0.5 to the power of 15 divided by 45. If we add this, this comes out to be 0.00109455. This is an estimation for the value of this definite integral. So you can see this is a very powerful tool, because here's an integrand that is very difficult, in fact impossible to integrate in terms of finding an elementary antiderivative, but we're able to apply the power series functions theory and an alternate series estimation theorem to find an estimate for the value of this definite integral. And we also know what the error of our approximation is. The error of approximation is less than 10 to the minus 7. So in summary, we have integral from 0 to 0.5 x squared times log of 1 plus x to the fourth dx. We estimate the value of this integral to be 0.00109455, and this estimate is accurate, so the error, absolute value of the error, is less than 10 to the minus 7. This estimate is accurate to within 10 to the minus 7. All right, thanks.